The model that I showed, it took like 1 or 2 days to run on our computers, but we came up with an equivalent, very simplified equivalent composed of some beam elements and some representation of the connection using spring elements. And you can see the comparison between the detailed and simplified model shows very good agreement between the two. This shows the temperatures and some of the sagging that was observed in one of the floors due to this elevated temperature and the thermal effects. And this is the global model. And again, I take you back to that picture. So the fire started from the north side of World Trade Center 1. This is where the aircraft impacted. And the fires went around the building until they were concentrated at the south side. This south side is facing the longer span of the trusses. And the trusses first started pushing outward, but then pushed inward and pushed this exterior wall inward until they created these large deflections. And now those columns that were subjected mainly to axial load are subjected to huge moments because of the P delta effects in addition to those large axial loads. And that's what resulted in the collapse of this building. And I'll show you here an animation. This is after aircraft impact. There was this system of hat trusses at the top that helped in redistributing the load of the columns that got severed in the core. And all the action carried on is in the north face of this tower, but now fires will be moving around. It will move this way to the east to west.
You drink some water, maybe?
No, ultimately they end up in the south, but I forgot whether they move east or west until they get to the south. And this is the south side now, and this is the panels that got dislodged by the effect of the aircraft. And you can see here now, because of the trusses that are pulling this inward, this is the behavior that you will get. And once that happens, this wall collapses and the tower falls afterwards. Same thing, similar behavior in World Trade Center 2, but remember the fire started and the impact started in the south face, and then next to it, we go to right away to the east face, which I cannot see. That's not it. Let me get out of this. But the east face is very close to the impact zone. The east face is the one that has long span trusses. So fire got moved here quicker than what happened in the south tower, and this is a third or fourth reason why this tower collapsed earlier. Now things are happening on the east side, and you can see the effect of that.
Ooh.
This east side is what is facing the long span trusses. The shorter span trusses were not as susceptible to this behavior as the long span. The long span trusses were 60 feet long, the short span trusses were 36 feet long. I know that you use metric systems, so I leave it to you as a homework to like the students use it. I'll skip that. And basically, once we identified the mechanism and why and how the towers collapsed, the question for us was what effect would that have in the construction industry? And NIST came up with a list of 30 recommendations for improvement to codes, standards, and practices in the US. And you can see this in our reports and our website. In terms of structural design, there were increased structural integrity requirements. Basically, we need more progressive collapse resistant structures in our country, especially for iconic and structures and tall buildings. Enhanced fire resistance of structures. Basically, we need to have a better handle on how to use fireproofing, its installation, inspection, and so on, adhesion to structural elements and so forth. And we need to move from the fire design being the responsibility of the architecture to being the responsibility of the structural engineer. Being able to analyze the structure and design the structure for fire effects, the same as we do for earthquake and for wind effects. There were a number of other recommendations for life safety systems, including active fire suppression, improved building evacuation, this was a huge one, and also improved emergency response. And then finally, some more recommendations related to practices and developments. Most of these have been already implemented over the past 4 or 5 years into our system of codes and standards in the US, in particular the IBC, the International Building Code, and this is just an example of what happened in 2007, where a lot of our recommendations have been accepted, including, some of these are big time changes, they're not small changes. An additional exit stairway for buildings, a minimum of one service, fire service elevator. Before that, we were not allowed to use elevators during emergencies and during fires, but now there is a provision in the code to allow a fire service elevator for tall buildings, increased wall stand for fireproofing, installation and also inspection, as you can see in the next slide, for fireproofing, and a lot of others. You can see all that on our reports on our website. But in 2009, there was another code change that adopted by IBC related to progressive collapse and structural integrity requirements. So that's what came out of this analysis. And with that, if you have any questions or if you wanted to read more about this, you can go to our website. It's listed here, and you'll find much more than what I just explained now. And with that, I thank you very much for your attention. So the second part of this presentation deals with the collapse of World Trade Center Building 7. As I showed you in the previous presentation, this was the building next or to the north of the World Trade Center complex. And that was not a small building, that was a 47-story building that collapsed in the same day around 5 p.m. or maybe a little bit later. And again, the same question we're trying to address here. Why and how did World Trade Center 7 collapse? Especially there was no aircraft impact in this one. Just as an introduction, I'm showing here an aerial photo taken from a helicopter about 14 seconds after the collapse of World Trade Center 1, the second building, it's a North Tower, the second building to collapse on that day. And unfortunately, you cannot see it properly here because of the resolution, but we have all this as very high resolution pictures in our computers. So when you see those arrows, you can see some steel panels, those exterior panels from the World Trade Center 1 collapse. They are here in this, close to those arrows that you can see, and they are part of the dust cloud. And we will talk about the effect of this debris coming from the North Tower on World Trade Center 7. But let me just say something before I start, that World Trade Center 2, the collapse of World Trade Center 2 did not affect or have any effect on World Trade Center 7 because it was more to the south, and the debris from that building did not reach World Trade Center 7. However, the debris from World Trade Center 1 reached, did some damage to World Trade Center 7, destroying some of the columns on the south and west perimeter, as I showed some pictures later. Let me just start with this, with this video, and we repeated it so many times throughout the presentation because this is a most clear video of the collapse of World Trade Center 7. And let me play it again, and I will show you. You will see here, a kink will start here first, and then it disappears when everything else is standing here, and then this portion will disappear and the whole tower or the whole building will collapse.
Wow.
So in the talk, I will be speaking first about similar to what we have done with the World Trade Center presentation, Towers presentation. I will be just providing an overview of World Trade Center 7 building design, and then the analysis sequence similar to what we have done for the towers, and then presenting the probable collapse sequence and the findings from all this, and then one new recommendation that we issued based on the analysis of World Trade Center 7 collapse. This was a 47-story office building located north of the complex, and you can see here its location relative to the World Trade Center towers. It was built on an existing Con Edison electric power station located on land owned by the Port Authority. And that fact, I'll show it in the next slides, resulted in a lot of design modifications to account for the fact that this building was installed or constructed on top of that electric power station. The building on 9/11, it burned or endured fires for almost 7 hours from the time of the collapse of World Trade Center 1 until 5:20 or 5:21 p.m. of that day. And that was the first known instance of the total collapse of a tall building, primarily due to fire. And I explain why that is the case. And you can see here, this is the north face of the building, and you can see the Con Ed station is situated underneath that building, and that resulted in some changes to the structural design. Similar to the towers, the way the building was structurally designed was to take all the wind loads by the perimeter of the building. So the perimeter of the building consists of moment-resisting frames, all the four sides. Everything inside the building, all the four columns, were just to carry gravity loads. As such, all the connections, if you are familiar with steel construction, all the connections on the perimeter are moment-resisting. All the connections inside the core of the building are what we call shear or gravity connections, which are much weaker than the moment connections. Moment connections are able to transfer moments to the columns to take the action of the wind loads. But shear connections are just sitting there to transfer the gravity loads to the exterior columns.